Hey, welcome back to the StackIt series. Last time we implemented this quiescent search for our alpha-beta algorithm, and we also discussed that maybe we want to write some front end. That would be nice, but I thought maybe it's better to stay on track what the initial idea was and then do the front end all the way at the end. So last time I already mentioned this article, General Game Playing with Monte Carlo Tree Search by Michael Liu. Feel free to read it, it's pretty good. It explains how Monte Carlo search works with its different stages. So first you have a selection stage where you basically expand nodes in a tree until you reach a node where you haven't done any further next steps. So initially you just start with the root node, then you pick some of the next steps, which would be, okay, we're in the root node, let's say this is all our tree, then we cannot go down any further. We pick one of the next nodes, which is called expansion. So in our case, from the root node, we would then maybe pick this one. Then we do some simulation, which is basically do random moves until you reach the end of the game, X times. Or here it says one simulated game is played, but you can also play more than one. And then you propagate the result of the simulation back all the way to the root, and then you start from the beginning, which would be, okay, now we already expanded this node, so we can either go down here and pick another of the child nodes, and then do expansion again, which means add it to our tree, simulate until the end, propagate, go back, go down again. This time you might pick the middle node, add it to the tree, simulate, back propagate, and so on and so forth. And then the way you determine which is the best move is like according to this formula. Yeah, back propagation. It's explained in this blog post. It's pretty good. Then also at the end he has a JavaScript implementation. If you're interested, he said this is heavily influenced by the other article, which I also want to cite here. So this is by Jeff Bradbury, written in 2015, Monte Carlo Tree Search, where he also explains the same concepts and also has a Python implementation. I'm gonna more or less, I don't want to say copy, but we're gonna re-implement it the same way that he does. I will try to actually check the methods that he has and basically implement the concepts myself, but like, take a look at what he's doing, not spend too much time debugging my own stuff. So he needs a board which has a start, returns a representation of the starting state of the game. He needs current player, next state, legal plays, and winner. I think we kind of already have this. Then he has a Monte Carlo class which takes an init, update, get play, and run simulation. And then he gets past the board. We will not have this in our init. So if we look at what we have in our alpha beta search, we have a method get best move time and get best move depth. We will probably just copy those two. And I already made a file called MCTS, Monte Carlo Tree Search. Tree search. I think we don't need this in Python 3. And then we paste our two methods. And this one doesn't apply anymore. But time, okay. What we want here, we want to div init self states is empty. And I actually, I will copy this later. So we will pass the board in the get best move time method, and we will update the stage. I don't think we need a separate function for this actually. The next thing he actually implements is a function called getPlay, or he starts implementing the function getPlay from which will calculate the best move, and it will basically run simulations until the time is over. So we do something similar. We import time while allowed time in seconds. Start time equals time. Okay. While start time minus time will be bigger than start time. Minus start time smaller allowed time in seconds. Something like this, I think. Self-run simulation sounds good. And we pass the board def run self board, and then here we will something like this, and here pass for now. So this will run simulations until we run out of time. Then he also introduces a max moves parameter. And then here, what does he do here? So in run simulation, he makes a copy of the current states. He takes the current state, or the last added state, and then for t in max moves, is t used somewhere? I'm not sure. He gets the legal place, he just randomly plays one. So run simulation will do our random moves until the end or until max moves is reached. So we know how this works. We can do possible moves, born possible moves for move, and no, actually we import random move equals random choice possible moves, board move, board winning player. If board winning player returns 1, 2, or 0. Player 1, 2, or 0. Okay. If we have a winner, then we're done. Break. Yeah. For in range max moves. Okay, I don't know. Zack. So this could be a parameter. We make it a constant. No, parameter is fine. Let's say we play up to 1,000 moves before we stop. Cool. This will now do board. Do I have a copy already? I will implement copy on my board because we do not want to modify the original board. I thought I have something like this from custom board. Def copy self I think something like this. Didn't I implement this in the rotate methods? Flip and rotate. Yeah. Na gut, I think we will need to actually refactor this soon. It's super ugly that we don't have a constructor. We do have a constructor. Why don't we use this? We return board from custom board, self board, self player, self current player. Why do we copy paste it? So we have to clean this class up. I also thought we might want to replace this class with a NumPy version, which will again speed up our search as well. Also, we should refactor this part where we, yeah, this will be a separate episode though. Okay, so run simulation, runs a simulation on board copy. This is okay. Next stage, states copy append. And then, do we really need this? I guess so. Let's just see how this continues. So then we also need to track how many wins and how many plays we have in each. Let me just use the picture. So here we track how often did we play this move, how often did we win. And for this we need to expand this a little bit. Let's see how this is done. What is states copy used for? Let me just see. Board winner in states copy. This is just a copy of the board, isn't it? Self plays. Visited states and player state. Maybe we don't need the states copy because we copy our board. Why do we need the current player? Because for him the way to represent a node in the tree is player and state. One thing we can already see is we actually, before we start, this is interesting. Okay, let's just expand equals true. We want to expand. This winner moves all the way to the end. Okay. And here, so first we make a move. Then we see if we were expanding. And we haven't initialized this yet, or haven't seen this yet. Then we set expand to false, we initialize this, we add this to the visited states, we change the current player, we check if there's a winner, and then at the end we need these visited states to check. Continue. Oh yeah. So we only track these records for okay, we run a simulation. We go in, we make a random move. If we haven't expanded anything yet, and the chosen play is not already in the place, and then we expand this. This is the expand phase. Afterwards, we cannot expand anymore. We just continue random playing until we find a winner. When we find a winner, we break. We then go to all the visited states in this series, and we say we increment the plays, and if the player was a winner, we increment the state. So, okay, let's see, we can do this. Self plays. I will just do it exactly like he did for now, and then we can see. Oh yeah, this needs to be initialized. Okay, we want empty dictionary. Self wins equals dictionary. Okay. If expand and not board to string, We just store the board string as our state because this is what our state looks like. In self place, we haven't played this before. Expand equals false. Then we expand it. We go now into the simulation phase. And we call it state, not state. Equals 0, play state, and wins equals 0. And then if board winning player, we break. And then here we would do, then we need to track all the states that we visited. Can we visit a state twice? I think we can for sure visit a state twice. Let me just think real quick. So what we want to do now is we want to keep track visits, state, attend, state. This is strange. So for state in visits, self place state plus equals 1 if board winning player equals oh god. Actually, our board string already contains the player that is currently playing. If we check how we do this, toString will not be the first number will be our winning player, but this is gonna be a bit ugly. What happened here? I don't want to go here, I want to be in here. Maybe we should actually also store both anyway. Let's do it similar to what he did. He only updates the player after, which is funny. So we go in the current player, we make a move. So technically it's the other players. It's the move I made. I have to think about this a little bit after, but he updates the player after. Board toString player, and here in the beginning he initializes player with current player, then he makes a move, board move, and then I want to encode this as a state, and we will make it board current player, board string is the state, player is board current player. Do we still need this? Nope. This doesn't work because I need the player from before the move. Okay. like this. And let's see why this is in a second. Player state equals player self wins state plus equals 1. Okay, so we come in, we haven't made any move. Then we make a move, which basically makes it the turn of the other player. Which means from the root node we moved one down. Then we save in our expansion the state, which would be I just made a move and now the board looks like this. And then when we are done, let's say this is the winning condition already, we break, we visited one state, which means we have a 1, 0, because the other player won. Okay. We will check this in a second. Player board. If we don't have any legal moves, we can just return. Get play. We're back to get play. This was run simulation. Now we're back to get play. In get play, we want to check. Why do we need state player? We need to get track how many games we ran. Move states. Okay, we will see. So, okay. Now we can run simulations. Now the time is over and we want to evaluate this. So first off, we need to say, this was weird from the beginning. Huh? Player equals board, current player. But we don't need to worry. This will not change our board state. Next thing we need to do is, we don't need this for now. This is just checking if there's only one move to be made, then we just take this move. And if there's no legal moves to make, then we can't return anything. So we, instead of like running the simulation over and over again, we can just return. Okay, we could do this. So moves equals board possible moves. If not possible moves, return. If then possible moves equals 1, return possible moves 0. So whatever, right? Then we do the simulation and he tracks how many games actually simulated. So we could also do this. This is actually good. And we print games. This is a good debug. We will run this in a second. And here he's actually calculating which move we should take. One thing I'm missing. Ah yeah, here it is. Ooh. Okay, this is okay. So initially, now we just check for the move with the highest win rate out of the moves that we currently have. So we actually have to make all of the moves. We have to make all the moves. Check which one in our wins and plays has the highest ratio of wins to plays. Okay. Move equals max. And now we build a list out of, first we need to create all the board states. Next states equals board, no, yeah, equals for move in possible moves, board move, move, board undo, and state equals for next states append. Maybe we can make this easier. Board to string. Okay, now we have all the next states, and then we want to have current player. We want to have the self wins player S divided by self plays player S for S in next states. Print. So actually, instead of doing the max here, we just rates, I don't know, sorted this one for in move in rates, print %win move. Okay, and then we return move max rates, return move. Okay, this should help us, and then we do if name. The episode is getting a bit long, so let's just see if we can run it. And for this, we will copy something from our game .py, namely this one. Let's just do this. Import from board, import board, zack. Monte Carlo tree search, MCTS dot get best move, board, and time allowed in seconds 60. Oh, let's, I don't know, 10. And then Python MCTS. Object has no attribute, run simulation. Oh yeah. 1 second. Oh. Yeah, if I break my class apart like this, this won't work. Key error. Okay, cool. Yeah, this is because I actually wanted to if state in self place, because we only want the okay, 1 second. We go in run simulation, board copy, and then line 70 here. After this change, it should not do this anymore, right? I didn't want to unpack this. Okay, of course we don't see anything now, so after 10 seconds it should finish. And then print the games for us. Of course, we did 124,000 games. And then here I have a key error because there is, of course, some states in place which are not in wins, and we actually I should double check how he did it, because I didn't see that he did anything special there. Cannot choose from an empty sequence. Run simulation. Okay. Yeah, let's do this. Somehow we seem to have run into a point where we cannot make any more moves, but the game is not finished. Okay, so this is also slightly strange. We should have actually here. Winning player, why did this not return anything? Winning player returns 2. Print board run. Oh god, oh yeah, that's not good. Okay, I know what happens. Okay, probably someone else saw it before, but we are actually not copying this. I think if we do something like this, it would be safer. So someone can call us with their own arrays and we don't change them. Cannot choose from an empty sequence. Cannot choose from an empty sequence. Let's see. See, this is already getting called with after the first run, this board changed. And I thought this could be fixed by because this is nested. Copy, keep, copy, copy, keep, copy, import, copy for now. Okay, this doesn't. They should all be same. They are same. Okay, ugly. This episode is slightly longer, but I at least want to have one full run. The next thing we will implement in the next episode, though, is we will implement this UCT. Where is it? UCB1, where we do not just randomly choose moves, but we choose them depending on how often we have been there. And yeah, float object not iterable. Okay, we can do this again. Rates is sorted. I don't know. Sorted returns me an array sorted. Oh, this is just the floats. Oh. And I have to zip it with the moves. Then I should store, append the state and the move. And then here I should, okay, we need to, oh no, I could remove this, anyway. Only 3,683. Oh yeah, before we did so many. Okay. 0. None of them ended, I guess. Let's go. This is not nice. I think we should yo, none of them ends if we do random moves. Okay, what we do here is we do max moves, and I think this might now be a bit funny. If board, okay. Now we go back to the heuristic and we say if after X moves, player add value at boxes for or something, boxes for player, boxes for player, board, boxes for board, other player. This is a function. No, it just returns the other player. Okay. Winner equals player and it's 0. No winner. No. Okay. Winner equals board winning player. If winner, we break. If we move to the end without breaking, we go here and we say if player equals board current player. Also, winner is the player with the higher boxes. Okay, if board for board current player bigger than board current player, and if, sorry, I'm going to explain this in a second. Here we do smaller board other player and winner. So what happens here? So if we finish the loop without breaking it, we will go into this else, and then we will check if the current player has more boxes than the other player, then the current player is the winner, otherwise the other player is the winner. Let's see if this helps us a little bit. It is strange that in 5,000 moves we will not ever finish once. Yeah, of course, now I need to here I need to change to winner, and then we're finishing up. Yeah. Okay, this still doesn't work. Then we will look into this into the next episode. See you until then.